Hey, it's me, it's your Pocket Tutor, and in today's lesson we're gonna talk about equilibrium of bodies. But in order to do so, we firstly have to introduce the concept of a point particle. So, a point particle is an idealization of body. It is used to represent physical object as an adimensional entity. What characterizes a point particle is that it is dimensionless, and any body can be represented with a point particle, as long as its size is much smaller than the environment where the body is. So let's consider this car here. This car could be represented as a point particle, so as a single point without any dimensions, as long as we're considering the car in a very big environment. So let's say that we're considering the car that is driving along a road. But if we're considering something inside the car, like the driver, well, we couldn't represent the car as a point particle. And this is pretty straightforward. Another concept that we have to introduce before talking about equilibrium is the rigid body. A rigid body is an object with a physical extension and that does not undergo deformations, whatever forces are applied on it. What does it mean? Let's consider, for example, that we have a pole, a rigid one, and is represented as a rigid body. And let's say that we're applying two different forces, like these ones. Well, now the pole cannot be deformed by these forces, so it will never be able to bend like this one. So this is wrong, because a rigid body can only rotate or translate, but it cannot deform. And now that we introduced with these two concepts, we can talk about equilibrium, starting from the equilibrium of a point particle. A point particle is said to be in equilibrium when the sum of all the forces applied on it is equal to zero. So, whenever the sum of all the forces is equal to zero, we've seen that the speed of an object is not changing. While for a point particle, this also means that it is in equilibrium. So if we consider this example of this point particle right here, and we're applying three different forces, F1, F2, and F3, well, the point is in equilibrium if their vector sum is equal to zero. And this is always true. But what if the point particle is not on a flat plane, but on an inclined plane? An inclined plane is something that we'll encounter often in physical problems. And the equilibrium on an inclined plane is always the same. The sum of all the forces must be equal to zero for a point particle. So let's consider this example here. Let's say that we have a point particle with a given mass. This point particle will have a weight that is given by the mass times the gravitational acceleration constant, and we can do the vector decomposition of this force, since we have to compute the equilibrium along the inclined plane. So we'll have the line that is perpendicular to the plane passing through the point particle, and the line that is parallel to the plane. And the composition of this vector will give rise to these two new vectors. Where this one will be the weight parallel and this one will be the weight perpendicular. In order to satisfy the equilibrium, we need that the sum of all the vectors must be equal to zero. For the perpendicular component, we've seen that we have the normal force. The normal force is the force that the plane is applying on the body to maintain this equilibrium, and it's always equal to the perpendicular weight. So this one will be the normal force, and we already know that the normal force is equal to the weight perpendicular. Now, in order to have the equilibrium, we need an equilibrium force that will be in this direction, and we can call it Fe. The equilibrium force must be equal and opposite in direction with respect to the parallel weight, and we will see that the equation to find the equilibrium force will be this one. So in order for the point particle to be in equilibrium, we'll need a force acting on the opposite direction of the parallel weight with this intensity. But how can we obtain this equation? The proof is quite simple. Let's consider of having a triangle of vertices A, B, and C. And let's consider a point particle here with its weight. And let's decompose the weight. So we'll have the weight perpendicular and the weight parallel. Now we have here another triangle that is D, E, and F, that is given by this one. And it's quite easy to see that this angle here is the same one of this one, and we can call it alpha. And this is because DF, the segment DF, is perpendicular to CB, and DE is parallel to AB. And therefore the two triangles are similar. If the two triangles are similar, this means that DE over AC is equal to DF over AB. And this is a property for similar triangles. Now, if we call AC the height of the triangle and AB as L, where L is this segment here, we can immediately see that DE is equal to DF, and therefore W, times AC, H over AB, that is L. And DE is this force right here, pointing downwards. Now, in order to have the equilibrium along the parallel direction, we'll need a force that has the same intensity of the parallel weight, but in the opposite direction. So we will need a force like this one, that we will call Fe, the equilibrium force, with the same intensity of W parallel. The intensity of W parallel is the length of DE, and therefore Fe will be equal to W, the intensity of the weight, times H over L. And so we proved the equation that we've just seen. Now, in order to explain the equilibrium of a rigid body, we need to introduce another concept. That is the concept of the moment of a force, or also called torque. This is because a rigid body, differently from a point particle, can also rotate, because a rigid body has an extension, while the point particle, as we've seen, is dimensionless. The torque of a rigid body is always defined with respect to an origin point that we will call O. And the equation to find the torque is this one. So the torque will be the force times the distance. This distance is considered to be the distance from the origin point O to the line passing through the vector F, like in this case. But let's say that we want to compute the torque for this force here, F1. Now the distance from the origin O to this force will be the distance to the line passing through the force. And in this case, this will be D1, and T1 with respect to O will be F1 times D1. And this is if we're considering a problem in 2 dimensions. But if we expand our vision in 3 dimensions, the torque becomes a vector. And if a body is subjected to forces leading to rotations on different planes, then the total torque will be given by the vector sum of all the torques acting on the body. This means that in 3 dimensions, the torque is a vector and is given by the cross product between the vector force and the vector distance. Because, as you can remember, the cross product will give another vector. And now we can finally say when a rigid body is in equilibrium. A rigid body is said to be in equilibrium when the vector sum of all the forces acting on it is equal to 0, but also when the vector sum of all the torques acting on it is equal to 0. And this can be summarized by these 2 equations. The Greek letter sigma, the capital sigma, means the summation. So when the summation of all the forces acting on the body is equal to 0, and if the summation of all the torques considered with respect to any point is equal to 0, then the rigid body is said to be in equilibrium. This means that anytime we are considering a rigid body, it's said to be in equilibrium if it's not translating and if it's not rotating. Only if both conditions are satisfied, we can say that it is in equilibrium. And this is always true, be it on a flat surface, on an inclined plane, wherever. These two conditions together must be satisfied. Now, the last concept that I would like to introduce for today is the concept of center of gravity. The center of gravity of a body is the application point of its weight. Like in this case, let's consider having any given body of any given shape. Every body can be decomposed in small volumes, and every volume will have his own weight. When we then put together all the small volumes, the application point of the whole weight will be the center of gravity. And this is it for today. So in summary, today we have seen the concept of a point particle, that is this dimensionless entity that we use to represent a body when the environment is much bigger than the body itself. We've seen what is a rigid body, that is something that cannot be deformed, can only translate or rotate. We've seen the equilibrium of a point particle, that is achieved every time that the sum of all the forces acting on the point particle is equal to 0. We've seen the equilibrium on an inclined plane and how to compute the equilibrium force that we need to obtain the equilibrium on that plane, which is given by Fe is equal to the intensity of the weight times the height of the inclined plane over its length. We've then seen what is the moment of a force, or also called a torque, that is given by T equal force times the distance. I forgot to mention that the distance of the force with respect to any point is also called arm of a force, and the torque in 3 dimensions is given by the vector T, given by the cross product between the force and the distance vector. We've then seen the equilibrium of a rigid body, which requires that the sum of all the forces acting on the body is equal to 0, and at the same time that the sum of all the torques considered with respect to any point is equal to 0. And eventually we've seen the concept of the center of gravity, that is the point of application of the weight of a body. And that's it for today. See you next lesson. Bye bye.